You know, we live our lives inside of networks, but what if I told you that so many of them, from the internet itself to our own social circles, are all shaped by a single kind of hidden rule? Well, in this explainer, we're going to pull back the curtain and see what it is.
Just take a look at this. At first glance, it just looks like a total mess, right? A random jumble of dots and lines. But here's the thing. This is a map of a real-world network, and it is anything but random. It has a very specific architecture, a hidden order that we see again and again and again in both nature and technology.
So, that's the big question we're tackling today. What is this hidden rule? What's the organizing principle that shapes these incredibly complex systems?
To figure that out, here's our game plan. We'll start with the most obvious feature you can see, the hubs. Then we'll get into their mathematical signature, and we'll unpack what scale-free actually means. After that, we'll explore the wild consequences of this structure. And finally, we'll wrap up with the key takeaways. Okay, first up, let's talk about the most striking thing about these networks. When you look at them, your eyes are immediately drawn to these few, absolutely massive nodes. It's a world totally dominated by hubs.
This slide shows you a tale of two different worlds. On the left, you've got the good old bell curve. Most things in life, like say human height, they all cluster around an average. You don't see any 70-foot tall people, right? But on the right, that's a power law. And it's a completely different beast. There is no typical here. Most nodes have just a few connections, but then you have these few superstar nodes with an absolutely enormous number of links. It's a total winner-take-all situation.
And to really get a sense of what a huge difference this makes, just think about the World Wide Web. If the web were a random network, the odds of finding a single web page with over 100 links would be 1 in a quintillion. That's basically zero. It would never happen. But because the web follows a power law, the probability is actually about 1 in 100. So hubs aren't just possible, they are absolutely inevitable.
So these hubs, they're the result of this very specific mathematical pattern we keep mentioning, the power law. Let's dig in a little deeper and see how this becomes the formal signature of these kinds of networks. So here it is, the official definition, and it's surprisingly simple. A network is called scale-free if the way that its connections are distributed follows the power law. That's it. That power law distribution is the key signature we're looking for. But that kind of raises a question, doesn't it? Okay, we see the power law, we see the hubs, but why call it scale-free? What does scale even have to do with any of this? Well, to really understand that, we need to take a quick but fascinating detour.
Believe it or not, the term actually comes to us from physics, specifically from the study of phase transitions, and it's an amazing analogy that really makes this whole concept click into place.
Okay, think about water turning into ice, or in this case, a magnet. When it's really hot, all the tiny atomic spins are pointing in random directions. It's totally disordered. But as you cool it down, they suddenly snap into alignment, all pointing the same way. That switch, it happens at a very specific temperature, what physicists call the critical point.
Now, this is where it gets really cool. Watch what happens as we get closer and closer to that critical point. We start to see these little clusters of aligned spins popping up. First, just small ones, but then bigger ones, and then even bigger ones. These patterns, these fluctuations, they appear at larger and larger scales the nearer we get to that tipping point. And right at that perfect critical temperature, this system is just wild. You have tiny clusters, medium-sized clusters, and enormous clusters all existing at the same time. There's no typical size, no characteristic scale. The system is, quite literally, scale-free. And that's the light bulb moment. A power law distribution means you have hubs at all possible scales, just like that magnet. All right, so our networks are scale-free. They have hubs of all sizes, just like that magnet at its critical point. But so what? What does this actually mean in the real world? Well, this architecture has some really profound and often kind of paradoxical consequences.
In theory, a power law can just go on forever. But hold on, real networks are finite, right? There's not an infinite number of websites or people. So in the real world, how big can we expect the biggest hub, the Google or the Facebook of any given network, to actually get?
Turns out we can actually estimate it. The size of the biggest hub comes down to two main things. N, which is just the total number of nodes in the network, and this really crucial number called gamma. Gamma is the exponent of the power law, and it basically tells you how common those superhubs are. And this little exponent, gamma, it changes everything. Yeah, the biggest hub always gets bigger as the network grows, but gamma tells us how fast. For most networks, the hub's growth is pretty manageable.
But if gamma drops below 2, something really weird happens. A single monster hub emerges that starts to suck up a huge and growing fraction of all the connections in the entire system.
Now, beyond just size, this hub-dominated structure leads to a fascinating paradox, one of both incredible strength and shocking weakness, which was documented in this foundational paper. This slide shows it all perfectly. Imagine just random failures, a few websites going offline here and there. Because most nodes have so few links, these random hits rarely affect anything important. The network as a whole is incredibly robust. But if you're smart about it, if you launch a targeted attack and take out the biggest hubs, you can shatter the entire network. The hubs are its Achilles heel.
And there's one more major consequence. These hubs, they act like superhighways for information. Instead of taking a bunch of little local hops to get from one side of the network to the other, most paths are just routed through these giant hubs. This shrinks the average path length dramatically, creating what network scientists call an ultra-small world.
Now, it is really important to pump the brakes for a second. It's easy to get excited and start seeing this pattern everywhere, but this is not a universal law. Not all networks are scale-free.
For instance, think about the network of atoms in a crystal, or a country's power grid. These are highly engineered, highly ordered systems. Every node has a very similar number of connections. There are no massive, unexpected hubs here. They follow a much more predictable and uniform pattern.
All right, we have covered a ton of ground, from power laws and physics all the way to how networks can break. So let's bring it all home and summarize the most crucial points to remember.
So let's recap this hidden rule. First, many of the real networks that shape our world are scale-free, which just means their connections follow a power law. Second, this rule inevitably creates giant hubs in a winner-take-all structure. Third, this gives them that paradoxical quality. They're super robust against random accidents, but incredibly fragile if you attack the hubs directly. And finally, those hubs act as superhighways, making our connected world ultra-small.
And all of this leaves us with one final and maybe one of the most important thoughts. This isn't just abstract theory. The internet, our economy, our social media, they are all built on this scale-free architecture. So if the very structure of our world is increasingly defined by these powerful hubs, the crucial question becomes, who controls them?